Hello and welcome to the CSES problem solving club meetup today. If you can hear me fine, please post a message on chat so that I'll know my audio setup is working fine. Yeah, thank you, Traxus, for the confirmation. Let us begin the next problem. Let me just rearrange my tabs here. Yes, I have the necessary boards with me. So today's problem is an interesting one. The title is digit queries. Consider an infinite string that consists of all positive integers in increasing order. So this is just a concatenation of all the natural numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have 10 here, and then 11, and then 12, and so on. And this is an infinitely long string. In theory, our task is to process q queries of the form, what is the digit at position k in the string? Will be given q inputs. So this first number is q. Will be given q inputs in this example 3. So we're given 3 subsequent inputs. Each one of them is the value of k. So in this, the question is, this input is asking the question, what is the 7th digit in this concatenated string of digits? And similarly, this one is asking what is the 19th digit. And some example answers. For 7, it is quite simple. Of course, the 7th digit is 7. Yes, one thing to note in mind, this is 1 indexed. So all these positions are 1 based, not 0 based. So 7th digit is 7. 19th digit is, so this is 9, and then 11 and 13, and then 15, and then 17. This is the 19th digit, which is 4, and so on. So that is the problem. And turns out we can do a little bit of analysis, and then we can find some nice patterns and then write the code for it. So let's take a look. So this is what we've got. We have so I've just written the same thing out at the top here. So this is 1 to 9, and then 10 to 99, and then 100 to 99. So what I've done with this over braces here is group them, group all these numbers by the number of digits in them, which I will also call as the width of the integer. So this, all these integers are 1 digit wide, all these integers are 2 digits wide, all these integers are 3 digit wide, and so on. And the one question that we can ask is, can we tell how many integers are there, or how many digits are consumed by this concatenation of all these numbers until the largest n digit integer? Let's call it that. So for example, these are all the 1 digit integers, and how many digits do they consume as a group? 9 digits, because each one is just consuming 1 digit. How about this? From 10 to 99, these are all 2 digit integers, and 99 is the largest 2 digit integer. So how many digits have they consumed? And that would be 2 times the number of integers that we've got here, and we have 90 integers. So 2 times 90 equals 180. And why is it 90? Because it's 99 minus 9, so 90. And similarly, we can continue just one more example. So here we have got 900 integers, because 999 minus 99 is 900, and each integer is 3 digit wide. So as a group, they're consuming 3 times 900 equals 2700 digits, and this continues. So we'll use this as the we'll use this observation as the basis of the solution. At least that's what I'll be discussing. That's how I have solved it. And I will call these numbers also as the peg numbers. So this is one peg, and this is another peg, and this is another peg. So given any k, we'll try to find one of these interesting numbers. Okay, and what are these numbers? So for example, so here we saw all these 2 digit integers consume 180 digits together. So how many digits have we consumed when we have reached 99? So we have consumed 189 digits. That is 9 plus 180 189. And similarly here we have consumed 2889 digits. And even this number here has a very nice pattern. So if you continue to the next number would be the number of digits consumed all the way up to 9999, that is the largest 4-digit number, would be 38889. So there's a nice pattern going on here. 9, this is 189, this is 2, then 889, then 3, 8889, and then the next number would be 4, and then 4 8s, and then 9, and so on. So a couple of things we'll do. One, we'll see if we can find a formula for this. And I'll do it in 2 steps. First, I'll find a recurrence relation. So I'll express this in terms of the previous number. So if this is an, I'll express this in terms of an minus 1. And then I'll also find the closed form expression. Okay. Although the recurrence relation itself will be enough to solve the problem, but I'll just, for the sake of curiosity, obtain the closed form expression too. So let an denote the number of digits in 1, 2, 3, and so on up to the largest n-digit integer. So this is the largest n-digit integer. For example, if you plug in 3 here, we get 999, the largest 3-digit integer. And A0 doesn't have a lot of meaning in this problem, but I'm just choosing a nice starting point, although this doesn't make sense in our problem because we'll always have at least one integer. But I'll just say A0 equals 0. So I can just assume that if there are 0 numbers, then they consume 0 digit. So that's the starting point. And then after that, we'll have this relationship. And why would we have that? Let's look at that. So if you see, this is 189. This is an minus 1. Let's say n equals 3. So this is a1, a2, a3. So this is a2, and this is, here we are dealing with 3-digit integers. So a3. So how much do we have to add to this number to get here? And we have to add this number, 2700. So that's the number we have to add to an minus 1 to get to an. And how do we get this? This is the width of the integers, that is 3, times 9 times 100. So that 100 is the smallest 3-digit integer. The smallest 3-digit integer. So that's how we are getting this. So 3 times 9 times 100. So it's written down here. This is the extra part. So that 3 is n. So n represents the width of this integer. How many digits are present in that integer? So this 3 is shown here, n, and the 9 times the smallest n-digit integer. That is, in this case, 100. So 10 to the 3 minus 1 equals 10 squared equals 100. So this is the recurrence relationship. If we know one an minus 1, we can get to the next one. Other way to look at it is an minus 1 would be this, the number of digits consumed by the n-digit integers. So once we have this, we can see that a1 is working out correctly. So this was a nice, elegant choice, I would say, for a0. And then a1 equals 9, and then we continue. So 9 plus the next thing that we want to do is 9 times 2 times 10. So 9 times 2. Okay, so 9 times 10 is written as 90 here. This 9 times 10 is written down as 90. And this formula works because we obtained it from this observation here. Let's say we want to also find the closed form expression, which is not necessary for this problem, but it's just good to know. We can use some of the arithmetic tricks that we've discussed in the previous session. So this is a similar trick. So let's say, so this is how an would look like. So an would be 9 plus 2 times 90. Basically this expression, this term being added n number of times, and this would be the last term. So that's how an looks like. So this part would be an minus 1, and then the lesser part would be an minus 2, and so on. So this is the full expansion given this an. And how do we find a closed form expression? There are many ways. Here's one way. So let's write down an equals 9 times the whole formula that we have got from up here. The only thing I've changed here is I've taken this 9 outside as a common factor because every term has got 9 involved. So I've taken the 9 out as a common factor. What remains is 1 plus 2 times 10 from here, then 3 times 100 from here because 9 has been taken outside, and so on up to n times 10 to the n minus 1. Okay, after that I can just multiply this whole thing by 10, and I think that is sort of a little bit of, that step requires a little bit of intuition and prior experience with solving problems like this. So I just went ahead and multiplied by 10 because I know when I start subtracting these two things, I'll get a neat expression outside. So that comes from intuition. If there's a better explanation, please feel free to share that. So what I've done here is an, and this is 10 times an. So, and I've just shifted the terms a little bit. So let me just show how I've just aligned them so that the terms are nice to look at. And we can see the cancellations, not really cancellations, we can see the subtractions easily. But let me explain it step by step. So when I multiply this expression here by 10, this one becomes 10, which I've noted down here. I've just shifted it to the right side for better alignment. And this 2 times 10 becomes 2 times 100. And similarly, this 3 times 100 becomes 3 times 1000, which is present in this dot dot dot. I'm not really showing that here. And similarly, there would have been term n minus 1 times 10 to the n minus 2 term here, which has been expanded and written down like this, n minus 1 times 10 to the n minus 1. And this term here has become n times 10 to the n because I'm multiplying this number with 10. And now when I do a subtraction, I subtract this equation minus this equation, we get something nice, and that is 9. This one remains as is. This becomes just 10 because 2 times 10 minus 10 is 10. And here again 3 times 100 minus 2 times 100 is just 100, and so on. We'll get 1000 and then 10,000, and this is again 10 to the n minus 1, and only this is negative sign. So this is one lone term outside here for which there is no term on the top. So this becomes minus n times 10 to the n. Now this thing we can easily find a closed form expression because what we have inside from here, from this 1 to this 10 to the n minus 1 is a geometric series. We can apply the geometric series formula. A little bit of cleanup from here to here. I'm removing 9 from both sides, and I'm removing the negative sign here and putting the negative sign here. So in other words, I'm dividing both sides by minus 9. So when I divide this side by minus 9, this becomes an. It has become cleaner. We are dividing this side by minus 9. So 9 and 9 cancel and one negative sign gets added. So this is how it looks. So all of these terms get a negative sign, which is shown here. The negative sign is put outside, and this negative term becomes a positive term here, n times 10 to the n. And now we can solve this. We know the geometric series formula for this. So this would be the common ratio. So the first term multiplied by, so the first term is 1 already. So that is invisible 1 here. And then in the numerator we have the common ratio raised to the power of n, because we have n terms here, minus 1 divided by 10 minus 1. And the 10 minus 1 is 9. So that's what we are seeing here. And then we can just rearrange these terms, clean it up a little bit more, and this is one formula that we get. So we take this in the numerator, so this term is multiplied by 9, so that is this term here, 9 times n, 10 to the n, and then we have 10 to the n and 10 to the n common in both these terms, which I take outside, and we get 9n minus 1, 10 to the n plus 1 divided by 9. Okay, so so one interesting thing here to note here is that this numbers are growing pretty fast. So for example, when we go from A1 to A2 and then from A2 to A3, these numbers here, this A1, A2, A3, they're growing really fast, and they're growing of the order, I would say, big O of n times this interesting number 10 to the n. So when we are going to take a k and find the spec numbers, so like I said, if I take a k, which I'll explain in the next board, and I want to find the spec numbers closest to that k. So that way, and we can do that in a really fast because these numbers are growing very fast. You can very quickly find these spec numbers. Okay, so I'll move on to the next board now, and that is where we'll discuss the solution, how we can use this, whatever we saw in this board to arrive at a solution. So let's see. So I'm illustrating a solution with a specific example. Let's say k equals 197. And let's just visually, as a human, see what the solution should be. So 197 is the question. We want to find the 197th digit. So this is 197th digit. We already know how to compute this. We can just convert this formula into code, and we can get these numbers quite easily. This 9 and this 189 and so on. So we know that from 1 to 99 we have consumed 189 digits, and we're asking what is there at 197th place. So what we will do, in the code we will find, or in the solution we'll find all these peg numbers, 9, 189 and so on, and we'll try to find the largest peg number that is less than our k. So that way we have arrived at the first peg. So this is our first milestone. So we know that there's a 99 here, which has consumed 199 digits. Now we'll just try to see how far we have to go from here to get our solution. So the next thing we can do is the next thing that we know is that these are all 3-digit integers, each one of them. So between this and this, how many full integers are present? That's the next question. So 197 minus 189 is how much? It is 8. So 197 minus 189 is 8. 8 divided by 3, because each integer consumes 3 digits here. So 8 divided by 3, if you do a floor division, then the answer is 2, which means there are 2 full integers here. So we have arrived at the second peg number. So I'll call this the second peg number. So the first interesting peg number was 99. The second milestone that we have reached is 101. By finding this difference, 197 minus 189, dividing it by the number of digits in each, that is by 3. And we know that there are 2 full integers in between. So we have reached this interesting number. The next question is, how many extra digits are there? So there is like a spillover. There are some extra digits still lying there, and how many of them are there? So 197 divided by 197 minus 189 is 8, and each integer is consuming 3 digits. So 8 modulo 3. So 8 modulo 3 gives us a remainder 2. So there are 2 extra digits unaccounted for, and that's it. So that would be the solution. So our solution would be, we know there are 2 full integers, and there are some digits spilling over here. So 99 plus 2 integers is 101, and then the next integer is 102, and we want the second digit of 102 as the answer. So that's how we'll get the answer 0. So the same things are explained, same stuff is explained here in these in this board, and I will be repeating. I will show 2 more examples just to in case if anyone missed anything. The second explanation, you can just pay closer attention to those steps. So but the reason I'll show 2 more examples is just to make sure that this technique works even for some of the corner cases that we might have to be careful about. Okay, so let us see the first illustration once again, step by step, like I've explained here, and this would become the template for the solution for the final algorithm. So the largest AI less than k equals 197 is A2 equals 189. So these are all, I'm calling them all AI, just according to the notation that we have established here, A0, A1, A2. So this is a sequence of, so this is, this one is A1, this is A2, A3. So what is A? Okay, I've not defined A anywhere. So I would say AK represents the number of digits consumed from 1 to the largest k digit integer. So for example, A2 represents the number of integers from 1 to the largest 2-digit integer, which is 99 here. And similarly, A3 represents the number of digits consumed from 1 to the largest 3-digit integer, which is 999. So that is the sequence A. Okay, so AI, so we will find the largest AI such that it is less than our k. So in this case, it is 189. And whatever that I is, the largest AI, we will just add 1 to it and call it n, because that represents the width of the integer that k is pointing to. So we have found this is A2. So this 2 is telling us that these are all 2-digit integers, and we have consumed 189 digits to reach all these 2-digit integers. So the number that we are dealing with, which is after this number, is certainly going to be a 3-digit integer. So that's what I mean by this. This notation is slightly loose. I'm not trying to make it too formal. So let us say the largest AI that we have found is this. Then we automatically know that our solution integer, the integer that will lead to a solution, is going to be 3-digit integer. So that's what I'm expressing here, n equals 3. The kth digit belongs to an integer with n equals 3 digits. The distance of the kth place from the a2th place is, so this is the a2th place, so the previous peg place. This is the place we are interested in. So the difference is 8, noted, and that means 8 divided by 3, 3 is our n, so 8 divided by 3, and the floor of that is how many full integers we have. Still our solution integer, I'll call this the solution integer for now, and this is the solution digit, that arrow, the digit that the arrow is pointing to. So the largest full integer, again loose terminology, the largest full integer on or before the kth place is 99 plus 2101, because we have established here there are 2 full integers, so 99 plus 2101 is the largest full integer either present on k itself. It is possible that k is pointing here itself, or maybe it is before that. And the distance between the end of 101, so this is the end of 101, and this is the place we are interested in. So the distance between this one and this place is the remainder that we had found earlier, so 8 modulo 3, because the complete distance was 8, and 3 times 2 were consumed by this thing, so 8 mod 3, which is 2, is the digits that are spilled over to this position k. So 8 modulo 3 is 2, so the kth place is the second digit of 102, thus the answer is 0. Okay, so that is one example. Okay, continuing. Let's take another example. So in this case, I've just chosen this example as another demonstration of the corner cases. So in this case, k points to a digit that is in fact the final digit of a full integer. So earlier we had k pointing somewhere in between an integer. So in this case, it is pointing to the end of the integer. So we'll do the same steps again and see how it goes. So k equals 195, and this is our peg number 189, and the difference is okay. And just like before, we conclude that we are dealing with 3-digit integers. Our solution belongs to this group of 3-digit integers, that is n equals I plus 1 equals 3, same as before. The distance between this and this place is 6. So 195 minus 189 is 6. And 6 divided by 2, because each integer, 6 divided by 3, because each integer consumes 3 digits, is 2. So 6 divided by 3 is 2. That tells us that there are 2 full integers from here to here. So that's how we come from 99 plus 2 and get 101. And then when we do a modulo, when we do 6 modulo 3, we get 0, which means that we don't have any digits spilling out. Our arrow is pointing, or k is pointing at the end of an integer. So there's no digit spilling over. So k is pointing to a full integer, the end of a full integer. So the distance between the end of 101 and the kth digit is 0. So the kth digit is the same as the last digit of 101. So as a human, we can make this conclusion quite easily that this k is pointing to the last digit of 1. In the code, we have to be a little bit careful. And there's a more elegant way to express this code, which I'll come to a little bit later. But the one thing that we have to be careful, as per the current analysis, is that if k is not, if the remainder, so the difference modulo n, the remainder is non-zero, which means we have to add 1 to what that interesting number that we have found, add 1 to it, and then find the digit inside it. But if this difference modulo n is 0, it means that we are already pointing to the end of that interesting integer 101, that second peg number that I was talking about. And yeah, I think those are the 2 interesting cases. There's one more I have worked out just to show what happens if we are pointing at the end of a group, and it works out the same way as we have discussed earlier. So I'll skip over this. I don't think this is very interesting, but in case, I mean, this thing only gives some sort of sanity check for this part, that we're taking, we're finding an AI that is less than k, not less than equal to k. So it is providing a sanity check for that. I'll just show how we get started, but skip over the remaining steps. So in this case, what would we find as the first peg number? So we will find this as the first peg number, because we're looking for the largest AI that is less than the number we are given. So here we are given 189, and the largest AI less than 189 is just 9. We start the solution from here, and A1 is pointing to the uh, to the last one digit integer. So our solution integer, which is this one, is going to be a 2-digit integer. So this logic still works, these first two steps, deciding the number of digits where our solution integer lies. Yeah, that is all. The remaining stuff is the same. So the general solution is going to work like this. Find the largest AI less than k, call it A max. Let n equals max plus 1. So A max, so this max is the, so in our example, it was the, for example here, it was A2. So it was pointing to how many digit integers we have accounted for already. So A2. So that is the role played by max here, the subscript. So n would be one more than that. That is where, so that represents the number of digits that belongs to our solution integer. Then compute the largest full integer on or before the kth place as follows. So p equals, this is the previous integer, this is that integer which looks like 99999. So this is that one, plus how many full integers do we have? That distance that we were talking about divided by the number of digits in each of those integers on the right side. So that I'm denoting with p here, and I'll be using the same variables in the code as well. And note that an minus 1 equals a max. So this number an minus 1 is the previous number, so a max, that first peg that we found. And we can write it as a max, we can write it as an minus 1. It does not matter, because this is the relationship, n equals max plus 1, which means max equals n minus 1. So the previous one, if I dealing with n, if our solution integer is n digit integer, so this is the n minus 1 digit integer, the largest n minus 1. So the digits consumed up to the largest n minus 1 integer. Okay, so we will use a subscript n minus 1 in the formulas for the sake of clarity, and then compute the distance between the last digit of p. So this is that second peg number. So here we have so if you go back to this example, this is our integer p, which we have arrived at by adding this one, which was expressed as 10 to the n minus 1, and yeah, so this is p. So understanding that is p, we want to compute the distance between the last digit of p and the kth digit. So how many integers have spilled over after the end of p, and that is k minus an minus 1 modulo n, just like we did earlier. Now if r equals 0, then the solution is the last digit of p, which means the arrow is aligned with the end of the second peg number. Otherwise, the solution is the rth digit of p plus 1. Okay, and this looks a little bit inelegant, but there's a way to clean it up. But this is how I started writing the board, and it worked out like this. But I'll just show in a second code example how to clean this up and make one nice single formula for this one. Okay, for now we'll continue with this slightly inelegant solution. So find the last digit of an integer. And how do we find the last digit of an integer? Because we have to solve this problem for this part. So how do we find the last digit of any integer? That is simply modulo 10. And this is pretty straightforward. For example, if you have a number like 5, 6, 7, 8, 9, we want to find this last digit, which is 9, which is to a modulo 10, and we get the remainder. How do we find the rth digit of an integer? Okay, so let's take this example. So how do we find the second digit of 5, 6, 7, 8, 9? So first we have to get rid of the 7, 8, 9. We just need to extract 56 out of it. And how do we do that? We do an integer division of this number 5, 6, 7, 8, 9 by 1000. So that's what we are doing here. We just get rid of the 7, 8, 9 and just keep 5, 6. And how do we know that this has to be 1000? Because there are 5 digits. We want to keep only 2 digits. So we want to get rid of 5 minus 2 digits. So that is 5 minus 2, 3. And that is what is noted here in the denominator, in the general formula. So n is the number of digits in this integer, in our solution integer. R is the rth digit we want to pick. So we want to keep the first r digits. We want to get rid of the last n minus r digits. So that is the denominator here. And once we have got this 56, we just want to pick the last digit of 56 because we are interested in the rth digit only. And that we already know how to do. We just do a modulo 10. So 56 modulo 10 gives us 6. So that's the modulo 10 we are seeing in this place here. Okay, so I think all the concepts are built. I'll quickly show the first solution and then how to tweak it to get the more elegant solution, especially the if-then part here. Okay, so let us go through the code, and I'm hoping this can be done in the next 8 minutes or so. Okay, I think I'll keep an example open. I think the example illustration is more easy to cross-check, more easy to use for cross-checking the actual code implementation with what we have understood so far. Okay, so let AI equals the number of digits in concatenation of 1 to 10 to the I minus 1. So here we are getting the input k, and we'll find a max equals the largest AI less than k. Set n equals max plus 1. Okay, this is just the commentary, same thing that you've seen here. Let's see the actual code. So 3 variables all initialized to 0, and this is the a next. So this part of the loop is implementing this recurrence relation. So we're trying to find the next a again and again, and we keep checking that it does not exceed our integer k, the given integer k. And the moment we see that it has exceeded, we just take this out. So this it has been written a little bit carefully so that because this a next can exceed the given k. So we are not setting, this is the number we are interested in. So we are setting this a max to this computed value only when we are sure that value is less than k. So it's just writing the code and arranging it properly, but nothing more going on here apart from just implementing this formula. So when we reach here, this place in the code, we have a max set properly. So set properly, I mean, it is in this example where we are given 197, a max is set to 189, this first peg number, and n is also set to 3, and that is being done here. So as soon as we have entered this thing, this loop, we're incrementing n. And yeah, I'll not explain too much about this. This is easy to verify on our own. So I'll just continue. So at this place, we have a max set to 189 and n set to 3. And then we just keep applying whatever we learned here. So we find this second peg number p, we call it p, and we want to set p to 101. And how do we do it? We first compute this 99, where 99 is this number. That is 999, some number of 9s, and the formula for this is this one. And I'm just using the inefficient, probably inefficient functions, but there are better power algorithms to do exponents, especially for integers, but I'm not using them because this is good enough, and I just wanted to focus more on the solution. This is 10 to the n minus 1 minus 1. So that would be the correct number of 9s that we are interested in. And this is the number of full integers. So the distance k minus this interesting number divided by the number of digits in our solution integer. So this is that. So in this case, it would be 2, and we'll go from 99 plus 2 to 101. So p is now set to 101. The r denotes how many digits have spilled over beyond the last interesting integer. So here we would get 8 modulo 3, because n is set to 3. 8 modulo 3 equals 2. So in this case, r would be 2. So when r is 2, what we want to do, we want to do 101 plus 1 to get 102, and then pick the rth digit out from there. So that is happening here. P plus 1 divided by the correct difference, that is 10 to the power n minus r, the thing that we explained at the bottom of this board, this part, and then modulo 10. And if r equals 0, then we just show the last integer. So meaning if this k is pointing somewhere here where the remainder would be 0, then we just show the last digit of that number, that integer. Okay, so this is pretty much the solution. The last bit of thing is, can we make this part a little bit more elegant? And the answer is yes, we can. So let's see. So let's see what I'm changing. So once I found this pet number, what I'm doing to make this more elegant is doing all the distance computation from this number, this digit, the one, the first one of this new group. So we have found the end of one group, so the first one of this new group, and from here we'll do the computation. So if you see, wherever we have this k minus a2, I'm doing k minus a2 minus 1, because the distance will reduce by 1 because I've come a little bit closer to k. So wherever we had k minus a max, I'm doing k minus a max minus 1 divided by n. So let us check this case. For example, if I'm doing from here, the distance is not going to be 8 anymore, the distance is going to be 7, and 7 divided by 3 is going to be 2, and then I will add that to 200, not 99. So because I'm trying to find the distance of my new number from 100, in fact from the beginning of 100. So the distance is going to be 7 because computing from here, and 7 divided by 3 is going to be 2. So 100 plus 2 will give me the exact solution number. So I don't have that problem of falling one number behind my solution number. So 100 plus 2 is 102, and then when I do a modulo, which would be 7 modulo 3, and that would be 7 modulo 3 is how much? 3 is 1, right? So that would be the index. So that 1 will become the index in the solution number to find the digit. So because we're starting from here, when we reach here, it's a multiple of 3, and again we reach here, it's a multiple of 3. So when you get 7 modulo 3 1, that 1 is pointing here, so 0 1, so index 1 here. And the same thing works out for other cases also. It is easy to verify on our own. So the solution looks like this. So I'll just go back once again. I'll just show what has changed. So here we had k minus a underscore max, and then again here we have k minus a underscore max. So all those things have become k minus a underscore max minus 1, and again k minus a max minus 1. So we reduce the difference by 1, and we're again dividing by n, modulo n, all that is fine. Here, instead of that 9999 number, the largest n digit integer, we are choosing the next number of 100. So this, we are adding this number of full numbers to 100, not 99. So that's another thing that has changed. Once again, let me go back to the previous solution. So here we were using 99 as our base, and then starting from there. In this one, we're starting from 100. Yes, and then we have a very simple solution. We can always work with p. We don't have to worry about p plus 1 at all, because this computation makes sure that we always land on the solution integer itself. And then here I'm just converting it to a string, just using the C++ standard library, converting the whole integer into a string, and then picking the rth character from that string. So converting this to 102, a string, and then picking the rth character, which is 0, returning a character, printing a character. Yeah, so that is the solution for this. And this brings us to the end of this problem, which is digit queries. We will meet again tomorrow. I'll just check if there are any comments. If you have anything more to share, please feel free to do so. I'll just take a minute to introduce tomorrow's problem, which is also quite interesting, and also show the place in the book where which discusses problems of this nature. So great paths, and yeah, so this has a very tight time constraint, and I have to fix my code. So I just wrote it a couple of hours back, and I have the solution. I just have to make it fit within the time constraint, for which there are some optimizations to be done. The one thing I do want to share is that if you've not seen this problem before, there's a very nice section here. Yeah, so part 1, chapter 5, and pruning the search. I will be going through this tomorrow, this few pages, but if you read this in advance, I think this problem would make a lot of sense. There are some ways explained here to prune the search. So here it involves recursive backtracking. So this is a grid walking or grid path problem. We just keep walking the grid without touching every cell, without touching any cell twice. So there are no intersections. We touch every cell exactly once, and we want to go from one place to another place. So in this case, from here to here. And the question is, how many such paths are there? And there's a little bit of twist, which we'll discuss tomorrow. So how many such paths are there? And this is again a recursive backtracking problem, just like the n queens problem. But the time complexity is huge, and it will not fit for a 7x7 grid. There's no way it will fit within 1 second of time if you just do a normal like a regular recursive backtracking. So here we have to focus a lot on pruning. Like whenever we see that we have reached a state after which there's definitely no way to get a solution, we start pruning those recursion calls, and that is how we optimize. And all those pruning techniques are given here for a maze walk like this. So optimization 1, optimization 2, 3, and 4. So 1 and 2 are pretty straightforward. These are the interesting ones, optimization 3 and 4. And it probably takes about 5 to 10 minutes to read this whole few pages. All the 4 optimization techniques does not take a lot of time, just 5 to 10 minutes, I would say, maximum. It's a very simple section. And knowing these optimization tricks can help a lot with this problem. So that's what we will see tomorrow. All right then, so with this we come to the end of today's meetup. If there are any further comments about this problem or the problem that we discussed today, we can do so in the IRC channel or the Matrix chat. Okay, so we'll end today's session here. We'll meet again tomorrow, same time. That would be 1700 UTC. Until then, take care and goodbye.